Okay, in this lecture, we're going to learn about how you can calculate the electric potential for a charge distribution. And we're going to do an example in a little bit, but here I just want to introduce the equations that allow you to solve for the potential rather than the electric field at a point P near a charge distribution. And it's important to learn this, exciting to learn it, because this is easier than solving for the electric field directly. So you can solve again for the potential, and then you could take the gradient to find the electric field. And so this is nice for problems where you cannot easily solve them using Gauss's law. Okay, so far we found the potential for a point charge, and a point charge only, okay, to be that V at some position R is going to be equal to 1 over 4 pi epsilon naught Q divided by our magnitude of our separation vector. Okay, and just to remind you guys how this goes, I'll just draw a little coordinate system here. So we can make sure we're all on the same page. Here we put our point P up here. This is where we're actually solving for the potential. And let's say we've got our charge over here. So this is our Q, right? And let's just go ahead and remember that this is going to be our R prime. This is going to be our R. And then our separation vector is going to be pointing from the source charge to our point P. All right. Okay, so this is what we use to solve for the potential at point P given this situation. A lot of the times when we've talked about this in the lecture, this has been just R, but that would be true if I took this Q and I put it right at the origin. So it just simplifies it a little bit, but in general, this is the equation that we want, okay? If instead we've got a different situation, if we've got a funky charged object, right? And we want to find our potential at point P up here, we're going to have to do some sort of integration. So if you guys remember, the electric field can be solved for using this integral here. Okay, and this is the most general one. It assumes you're given a volume charge density rho. Okay, but we can transform this into an integral that's appropriate for a situation when you're giving a surface charge density or a linear charge density. Okay, but we'll start out here. And what we want to do with this is we want to use it to derive a similar potential equation for the potential. Let's examine what happens when we take the gradient of 1 over our separation vector. Okay, I'm going to argue that that is equal to the negative of our r hat vector divided by our magnitude of the separation vector squared, okay? And why is that the case? Well, if I look in the back of my book in spherical coordinates, okay, the r component of my del operator is just the partial derivative with respect to r. So if I apply that to 1 over r, okay, I end up getting right? If I do that partial derivative, I get negative 1 over r squared times r hat. Okay, so this right here is, this guy is our component of our del operator. Okay, so what does this allow me to do? The fact that the gradient of 1 over our separation vector is equal to negative r hat over the magnitude of the separation vector squared. Well, notice that that bit is in there. So now I'm going to rewrite our electric field integral with that little chunk in there. And that gives me prime negative 1 over separation vector, okay, d tau prime. Okay, so now let's examine this a little bit more, okay? If I look at this, this is the charge density. This doesn't depend at all on basically the position where you are evaluating the field. It doesn't care about it. So it only cares about the primed coordinates. It does not depend on unprimed r. Okay. All right, so that means that I can pull our del operator out. Okay, so that's what I'm going to do. So now I'm going to take the right-hand side. I'm going to pull that del operator all the way out of the integral. And in fact, I'm even going to pull it outside of this constant. And you'll see why in a second. This is still a volume integral. This is rho prime divided by okay, and I also needed to pull a negative sign out of here. Okay, why did we do that? Well, now if I look at this, this whole bit here has to be equal to the potential because, right, the left-hand side here is still the electric field, and we know that the electric field is equal to the negative of the gradient of our potential, which I'm going to go ahead and write, right? We can define our potential to be with respect to r. Okay, so now I can write just this bit as being equal to the potential. So if I wanted to calculate the potential directly from a charge distribution, I can do it by evaluating this integral here. Okay, and in a lot of ways it's going to be similar, I'll show you, to how we set up the integral before, but this is easier, okay? This is easier and the reason for it is because you don't have to worry about components when you're doing the integral. Essentially, there's not 3 integrals to solve. You don't have to worry about vectors canceling out. You can do the hard part, which is the integration, and then easily take the gradient to find those 3 components. Of the electric field. Okay, so that's exciting, I think. You can, just like for a electric field integral, you can replace, depending on the particular problem, the rho r primed, d tau primed. You can replace that with a similar infinitesimal charge, which is appropriate when you're giving a surface charge density, and you can also replace it with this if you're given a linear charge density.